Hi again, class. It's me again. Probably tired of seeing me at this point, but you got like 30 more of these to go, so let's just get going. We were talking about the fundamental theorem of calculus last time, parts 1 and 2, and before I move on to the next section, I want to give you like an example that kind of puts both of the, fundamental theorem of calculus, part 1 and 2, together for like a really nice example. So let's suppose the problem asks you to do this. It wants you to find this guy. Okay. Okay. So if we call this g of x, remember this is kind of the standard notation that we were using last time. Is if you call this thing g of x, then we want g prime of x. Or in other words, we want the derivative of this guy. Just writing it in all these different forms, just so you can see. And yes, this is the trigonometric function secant. I know bad handwriting, so just to clarify. Okay, so originally the fundamental theorem of calculus part 1, if you remember, this was not an x to the fourth, it was just an x. So you should be suspicious as to whether or not, this is as easy as you think. Had this been just an x, this would just be secant x, done. Okay, but it's not. It's close, but there's a little extra piece, so the fact that it's x to the fourth does change something. So first, let's in general find out what this is. The fundamental theorem of calculus part 2, FTC 2, tells us that this integral really is what? We're taking the derivative of capital F of x to the fourth minus capital F of 1. Right? Because FTC 2 says this. Says if you have the integral from a to b of f of x dx, this is equal to this. So you find the antiderivative and you take the difference of the value of the antiderivative at the endpoints. Well, this does not have to be a number, It could be an arbitrary thing. So at this point in time, it's some number x to the fourth. We don't know what x to the fourth is because x is a variable, but that's okay. In a sense, it's still a number. If you fix x, then this is just a number. So if like x is 2, this is 16. So the FTC 2 tells us this, that this is the antiderivative of this function, whatever it is, whatever that antiderivative is. It's capital F of x to the fourth minus f of 1. Okay? And then, because of the derivative properties, we know, this is the same thing as the derivative of the first guy minus the derivative of the second guy. Okay? Now let's think about this for a second. The FTC 1 tells us that the derivative of the antiderivative should just give us the original function, right? We discussed this. We said that if you take the derivative from a to x of this guy, this is essentially the antiderivative in a sense. If you take the derivative of the antiderivative, you just get back the original function. Okay? So what this means is, what I'm trying to tell you is that essentially we know that f prime of x equals f of x. But we're not just taking the derivative of f prime of f of x, big capital F of x. We're doing capital F of x to the fourth. So if you remember from Calc 1, there's this thing called the chain rule that you have to use when you deal with this scenario. So really what you're doing, what the chain rule says, is you take the derivative of this guy, so you find f prime. So the derivative is f prime of x to the fourth, but now you have to multiply that by the derivative of this inside. That's the catch. Normally, if our function was just f of x, then this derivative would be f prime of x times the derivative of x. But what is the derivative of x? It's just 1. So this would just be f prime of x times 1, which is f prime of x. You know, this is just 1. So the chain rule always applies in a sense, actually. It's just you don't really see an effect because the derivative of x is just 1, so you don't ever see any big difference. But in this case, it is going to make a big difference because this is x to the fourth. So we get f prime of x to the fourth times, now the trade-off was we have to multiply by the derivative of the inside function as is stated when you first learn the chain rule. And then let's think about what this is. What is f of 1? Well, f is a function. Capital F is a function. So if you stick 1 into it, you just get a number, right? And then what's the derivative of just a constant of a number? It's 0, so this is minus 0. So then this gives us f prime of x to the fourth times this derivative is 4x cubed. And then last but not least, what did we talk about? We said that f prime of x is just secant of x, right? That's from FTC1. The derivative of the antiderivative is the original thing. Okay, so this in some sense was the antiderivative, so when you take its derivative, you just get secant x back. And then, so what is f prime of x to the fourth? Well, if you replace this with the x to the fourth, you replace that with the x to the fourth. So this is secant of x to the fourth now instead of just x times 4x cubed. So this is the final answer. Okay, so this is there's a lot of concepts going on here, understandably, so this is a really good example to sit there and think about and definitely ask me questions about later. And a larger challenge now is we can actually make this not be a constant anymore either. We can maybe say this is 2x now. And try and think about what would happen to this had this been 2x instead of 1. That's something for you guys to think about, but we can discuss that definitely later. Okay, so this kind of brought FTC1, FTC2 all together in a very novel and challenging way. So definitely we're going to look at this again. Okay. So now that we have a lot of the theoretical aspects established, we can start to see how we're going to compute this stuff. How do we actually find these things? How do we find the antiderivatives easily? And how do we make sense of them in like real life scenarios? So this is going to be the content of the next section, which is 4.4. And now it's indefinite integrals. So we had definite, now we have indefinite integrals, and net change, and then I'll have to squeeze this, the net change theorem. So the net change theorem and indefinite integrals. Okay, seems kind of daunting, but we've already established everything we need to basically talk about this in a pretty painless manner. Okay, so first notation, basically, is we need to define what the indefinite integral is. The indefinite integral written okay, so notice normally we would put like a and a b here, right? If we have an indefinite integral, we do not write that. So a definite integral has a definite interval in which you're finding the area. An indefinite integral does not have that. It's kind of just arbitrary. So we just write it like this without the limits of integration. This is literally the antiderivative. Okay, so yes, it's literally the antiderivative. So if you take the derivative of this guy, the indefinite integral, you just get back the original function. Meaning, so this is like the takeaway. The antiderivative of f is the indefinite integral, it's capital F. That's what they're equal to. Okay. And remember, in general, when you take an integral, you can get a plus c, right? So maybe let's refresh some of the rules that we established with the antiderivatives right before, at the very end of Calculus 1. So there's a bunch of different ones. And these are the things whose antiderivatives or integrals we actually do know. So, and some of them have like names. So one is the power rule. Just like with derivatives, there's a power rule. And we talked about this last time. Is the integral of x to the n is this. As long as n does not equal -1. Okay. Because see now, the idea is that if we take the derivative of this, because this is like capital F. This is capital F of x. F prime of x should be the original function f of x. This is f of x. Is this true? Is this true in our case? Well, let's see. If you take the derivative of 1 over n plus 1, x to the n plus 1, this is a constant, remember, so you can just pull it out. So this is the 1 over n plus 1 times the derivative of this. And then this is, so 1 over n plus 1 here. It's the same. Then you just use the power rule here, right? So the power rule says bring the n plus 1 down and then subtract 1 in the power. So you minus 1 there. And then so this, so what happens with the n plus 1s? These cancel, and then you're just left with x to the n. So yes, this is true. This is definitely true. And that's what we mean by the antiderivative or the indefinite integral, which once it becomes clear in the context, you won't say the definite integral or the indefinite integral. You'll just say the integral, and people will know what you mean based off the context. So essentially what this summarizes to is the power rule. So is the integral of x to the n is this. So we now know the antiderivative of such a thing. So if we want to know the area under the curve of any function of this form, we can very easily get it. Very, very easily. Okay, so there's that. And then there are, you know, many functions other than just functions of this form, namely like trig functions. So we need to think about maybe those. So this is not a rule, it's just an observation. So what is the integral of sine x? So what is the antiderivative of sine? So this has to be a function whose derivative gives you sine, essentially. So you have to think, okay, this needs to be equal to some function whose derivative is sine. Well, I think negative cosine does the trick, right? Why? Why does negative cosine work? Well, what's the derivative of negative cosine x plus c? Okay, again, if you use the derivative rules, this is going to go to 0, right? Because the derivative goes to each piece, that's 0, so who cares? And then what's the derivative of cosine? It's negative sine, so this is negative sine x, which is sine x as needed. So that checks out. That's good. That's very good. And then if we got sine, we should ask what cosine is. Okay. Now if you think about this, this should just be sine, right? If you take the derivative of sine x plus c, this goes to 0, and then the derivative of sine is cosine. So that's good. Next up is secant squared. Yes, okay. So what should this be? Okay, maybe it's been a while since you've done trig derivatives, same as me, same for me. So I had to think about this for a second. But if you remember, tangent x, what's the derivative of tangent? The derivative of tangent is secant squared. So very good. So the derivative of tangent is secant squared, meaning that this is true. Because the derivative of this guy needs to be this, which it is. Okay? So you might ask, well, what's the antiderivative or what's the integral of just secant? That is a much harder question to answer, actually. We'll need to develop a lot of tools to answer that question. So for now, it's I don't know. We only know secant squared. And you can already kind of start to see maybe how the integration process is a lot more difficult than differentiation. With derivatives, all of the rules you learned in Calc 1, they allow you to take every single derivative you could ever hope for. Integrals are much harder, and there's like even competitions for figuring out some crazy integrals. So the process of integration is much more difficult, and maybe this will already start to show you why, but you'll see a lot more in the coming weeks. You'll see a lot more than this. Okay, and then we can, so what's some more trig stuff that we know? Okay, so let's say, what's the derivative of secant? Remember, this is secant x tangent x, right? So we know that the integral of secant x tangent x should be secant x. That's another thing we know, right? Because we know that if we take the derivative of this, we get that back. So this will be true. And if this is kind of a nice way to think about it is, you know, if you were to take the integral of both sides, remember the fundamental theorem of calculus is essentially telling you that the derivative of the integral just cancels out. So this is just secant x, and this just stays. So you can kind of see where this is coming from in a sense too. It's just the same way of thinking but backwards, but it all still works out. Okay, and then we got two more trig ones. Okay, so now do you remember what's the derivative of cotangent? It's negative cosecant squared, right? So we know that the integral of negative cosecant squared x is cotangent x plus c. Okay, and then, you know, this works, but if you don't want the negative sign to be here, you can multiply both sides by -1. So I'm just trying to have it in the way the book has it, just so it's not confusing. But if you remember, you can multiply both sides here by -1, basically. And that'll get rid of the minus sign here, and it'll just turn that to be negative. So it's not too big of a difference. And you might say, well, this plus c will turn into a minus c, but it's an arbitrary constant. It doesn't really matter at the end of the day. If it's positive, negative, it can be any number. So this will be, let's just fix this then to have it the way the book has. Cosecant, so this will be negative cotangent plus c. Okay, very good. Then what's the last one is, what's the derivative of cosecant? This was negative cosecant cotangent, right? So in a similar way, we know now that the integral of cosecant x cotangent x is going to be negative cosecant x plus c. Okay, and definitely think about this for a little bit. You probably haven't done derivatives in like a few months or something, so with calculus or math in general, it's all about practice. Practice, practice, practice. Okay? So we have these guys here. Now, essentially, with these and the properties of the integral that we have, we can now start to find some, the antiderivative or integral of some pretty interesting things. So let's do that. Example. Let's say we want this. Okay. So step one is, remember the rule that we had about the integral is if you see like a plus or minus sign, then you can break up the integral. So this is going to be the same as the difference of these two integrals separately. So that's using one rule already, which is nice. And then remember the other rule, it said if you have a constant out in front of your function, you can pull that constant in front of the integral. So this is just the same as 10 times this guy minus 2 times this one. Okay, and then now these guys here, just this one and this one, we've talked about how to find the antiderivative. So this here is n, in this case is 4, so we get 1 over 4 plus 1, remember n plus 1, times x to the 4 plus 1. That's the power rule. and then minus 2 times, what was the integral of secant squared? So remember, the derivative of tangent is secant squared. So this thing should be tangent, right? The idea is, if we take the derivative of this, the final answer, we should get this back, which will be a nice check. We'll do that. And then, of course, we have a plus c here. Overall is a plus c. You may say, oh, well, does this one give a c and this one gives another c? Yeah, like this one could give a c1, and this could give a plus c2. But when you combine these, you can just call that whole thing c. Because again, it can be any real number. So it really doesn't matter. So might as well just make it one thing c. Okay. And so, okay, that's 5, right? So 10 over 5 is 2. So this is 2x to the 5th minus 2 tangent x plus c. Which this is very amazing, because now if we did give limits of integration, like let's say 0 to pi or something like that, or 0 to 1, then this could give you the area perfectly, like perfectly underneath the graph. Well, secant's a little tricky. It has an asymptote at pi over 2. So going from 0 to pi, we'll talk about how to deal with things that have asymptotes and the area under their curve, but it's just an example. Let's just say 0 to 1 so you don't hit the asymptote. This will help you find the exact answer very easily. All you would have to do is just stick 1 into this, find a number, and then stick 0 into this, find another number, and subtract those two, because it would be f of b minus f of a. So this is an astounding result. Like, it's crazy that we can give you the answer for the area perfectly. Okay, and then let's check whether this is true or not. So this is essentially the antiderivative. So what is f prime of x? What is the derivative of this? Well, the first one, use the power rule. Bring the 5 times 2 is 10. X to the 4th when you subtract 1. Minus, like we said, the derivative of tangent is secant squared. And then the derivative of c is 0. So yes, look at that. F prime of x equals the original f of x. So this is perfect. We're set. Okay, now let's do maybe some more challenging ones. And this one's nice because we have a little change of variable. So let's say cosine of theta over sine of theta. Okay, so this is my integrand. And in this case, should I put dx? What should I put there? Well, these functions, their variable is theta, so I must put d theta. Remember, it doesn't matter, but it has to be consistent. Okay, and now you might ask, well, we didn't talk about any of this. Like, what is this? Like, this is crazy. Oh, sorry, this is the sine squared. My bad, I was gonna say this might not work out so well. Okay, so we have cosine over sine squared. So this first step is to make this, maybe, in trig you can write things in many ways. So let's turn this into cosine theta over sine theta times 1 over sine theta. And this is where, like in trig, when you do all these identities, like show that this equals that, this is the identity, and you'd be like, who cares about any of this? Well, this is like, those techniques are getting used right now, very, very immediately, because see how we're breaking this apart and turning it into something else. That's the identities right there. So cosine over sine is cotangent, and 1 over sine is cosecant. oh sorry, I wrote x. So now we have cosecant, cotangent, or cotangent, cosecant. So what should that be? What was the antiderivative of cosecant, cotangent? It was negative cosecant x, correct? And then again, I've been writing x so much, this should be theta, right? Negative cosecant theta plus c. So this is again the antiderivative. Okay, maybe let's do another example. Keep it going. And now let's actually find a definite integral. Let's actually find an area. And remember, we actually did this. This was an example where we used Riemann sums and we got an answer. Let's see how good the answer was. Let's think about how well it compares. What the Riemann sum gives us to the exact answer. Okay, again, there's a minus sign here, so you can split this up into two pieces. Okay, and then this one's ready to use. Power rules, right? You just use the power rule. So this will be 1/4 x to the 4th. And remember this notation, evaluated from 0 to 3. Minus, and then, you might have caught on to this already, but I'm just going to write it out in gory detail. Right here. And then, what does this give us? So, this chunk here, right here, I'll say that this is blue. Remember, is just 1/4, so you stick the first number in, 3 to the 4th minus 1/4, 0 to the 4th. F of capital F of B minus capital F of A. So that's what that term is. The underlined blue term, all of it gives that. So this entire thing, we're going to be subtracting from. And now, what is the antiderivative of this? Well, it's going to be x squared over 2, right? Because there's a 1 here. There's an imaginary 1 here that you don't always see. So this is going to be negative 6 x squared over 2. Because maybe I'll write some more detail. So this is negative 6 times 1/2 x squared, right? Because to the 1 up here, you add 1 and divide by that same thing. Okay, and then this is the same thing as negative 3x squared. So this is just minus 3x squared evaluated from 0 to 3. Okay. Now, this is just 0, right? And then 3 to the 4th is 64. Divide that by 4 is 16. So we have 16. It's 3 to the 4th. No, sorry, it's 81. Can't do math. I'm very bad at mental math, as you'll see. So yeah, it's 81 over 4. And then this is going to be minus, okay, and then let's work on this separately. So minus, we got to put this entire expression in parentheses. So whatever the outcome of this is, that's what we take this minus. You might be able to do this very quickly, but this is just for detail again. So this is minus. So since I have the minus here, I can just treat this as a positive 3 because the minus is already taken into account. So this will be 3 times 3 squared minus 3 times 0 squared. Again, capital F of B minus capital F of A. And again, this is 0, so this is just 81 over 4 minus, that's 0, and then this is 3 cubed essentially, so 27. And then this, once you do all the whatnot, this gives negative 6.75. So this is the exact answer, in which we got a pretty decent approximation to using, I believe it was 6 rectangles. And I think we used the midpoint maybe? Yeah, I think we used the midpoint, so we had 6 rectangles. But this is the exact answer. You can compare that to the approximate one that we got. Okay, so we're seeing how the fundamental theorem is used. So then, this has been some nice examples here. And then last but not least, let's do maybe one that seems at first very difficult. So we can do the, so this is another one. I'll just do it and then show you what I'm talking about later. Say we have that. Now notice these are t's. See t's here? That's got to be a t. Okay, now you might think, which one of the rules is this? Like, this is crazy. There's no way I can do this. Well, this t squared can divide into each 3 of these pieces. So, again, you might have to do some algebra before being able to use these rules. So, this is 2t squared all over t squared plus t squared over root t minus, right, the t squared can break up into each piece. Because, these all have the same denominator. You can combine them to get this back. So these are equivalent things. Now we have 1 to 9. Okay, so what's t squared over t squared? That's just 2. And then these t squareds cancel to just give root t. And then this is just minus 1 over t squared. Okay? And now you still may say this kind of, we never talked about how to do square roots or 1 over t squared. Like, this is some crazy stuff. But there's ways of rewriting both of these terms where it's just going to be t to some power. And then we could use the power rule. So, and then we can go ahead and break these integrals up because we have a sum and a difference. So the first one is just this. The second one is this. Okay, instead of writing root t, I can write t to the 1/2 power. Now we could use the power rule, and then minus. And then instead of writing 1 over t squared, I can write this as t to the -2 power. Okay, so look at that. All this algebra from way back when coming in handy. Okay? Now, there was a rule for how to deal with this, There's a rule for what the integral of a constant is. It's just a constant times 9 minus 1, so 2 times 8. But in terms of the integral of a constant, notice that a constant is the same thing as a constant times x to the 0, right? Because what is x to the 0? It's just 1. x to the 0 with power is just 1. Now you may be like, well, what if x is 0, so you have 0 to the 0? Let's not complicate things. Let's just think, this is a good way to think about it. So if you apply the rule, the constant will come out, right? So you just have constant times the integral of x to the 0 dx. And now you can apply the power rule. So this is constant times 1 over 1 plus 0 x to the 1 plus 0. Well, okay, 1 plus 0 is just 1. So 1 over 1. And then x to the 1 plus 0 is just x. So this is just a constant times x. That's all you get. So the moral of the story is the integral of a constant dx is just cx plus maybe some other constant c1 or something. Who knows? Or d, capital D, who knows? It's just another constant. So all it's saying is it'll turn into a linear function. This is like the equation of a line. Okay? So, moral of the story, after all this detour, is this integral is just 2x. So this is 2x evaluated from 1 to 9 plus, and then, okay, how do you do this? So this is t to the 1/2 plus 1 times 1 over 1/2 plus 1. All right, that's what the power rule says. Okay? Well, what's 1/2 plus 1? It's 3/2. So we have 1 over 3/2 times t to the 3/2. And if you have 1 over a fraction, it just flips it, right? So this is 2/3 t to the 3/2. And you can check that this derivative is just t to the 1/2 power, which is the square root of t. So this derivative is that. So it is the antiderivative. Right? Because if you take the derivative, you get 2/3 times 3/2, bringing the power down. And then you get 3/2 minus 1. This cancels to just 1. And 3/2 minus 1 is that. So perfect. Okay. So we have this. So 2/3 t to the 3/2. That is evaluated from 1 to 9. And then last but not least, minus, okay, let's do the same thing here. We have t to the -2 plus 1 all over 1 times -2 plus 1. That's what the power rule says. So then this is just -2 plus 1 is -1. So we have 1 over -1, which is just like -1, right? So you can just put a minus sign. So this is minus t to the -1. Or another way of writing that is -1 over t, right? Because ignore the minus sign. T to the -1 is just 1 over t. So we have this minus sign originally, and then this minus sign hits it again, so it actually becomes a plus. So it's just plus 1 over t evaluated from 1 to 9 again. Okay. So then, doing each of these in chunks, this is going to be 2 times 9 minus 2 times 1. That's this piece here. Maybe I'll color code it. So this is the blue piece. And then plus 2/3 9 to the 3/2 minus 2/3 1 to the 3/2. So that's this piece here. And then plus 1 over 9 minus 1 over 1. That's last but not least this piece here. So that's how, that's what this symbol means. This vertical bar 1/9. Okay, and at this point, you just figure out what this is. I think it's a waste of time for me to do it. I'll probably mess up too at some point. But apparently it gives you 32 4/9. That's what the answer ends up being. I guess the only tricky thing is, what is something to the 3/2 power? Remember, this means you take the square root of this number and then you cube it. So you would take the square root of 9, which is 3, and then cube it, which would give you 27. So that might be the only tricky part, but it's just arithmetic at this point. And this is, again, amazing. This is the exact area under the curve of this very complicated function. So, I mean, beats doing Riemann sums all day. Okay, so now that we've seen how to actually feasibly find the area under the curve, without resorting to a computer, because computers can do things really fast as long as you program them right. Well, that's its own field of math. We're not concerned with that right now. Some of you may do that as your job in the future, who knows, but it's not today. We're going to get to the net change theorem. So, net change theorem. Okay. And the net change theorem, I mean, we've already seen it, is basically what the fundamental theorem of calculus is telling us. It's this, is that this guy here is equal to that. So that's all it's saying. That's the fundamental theorem of calculus. But if we associate, if we give a physical meaning to what the function is, then this has a very powerful, application. So what this is telling you basically is that, here's your guy here. Let's say you have this physical quantity. Or actually, let me make this related to our lives today. So say f of x, this is, and let's use t here for, so again, I said you can replace this with a t, doesn't do anything. So f of t, this is the number of deaths from coronavirus. Okay, so this is representing the number of deaths as a function of time. So, day 1, day 2, day 3, day 4, whatever day 0 is, I guess whenever you start counting. So this just tells you the number of deaths. So what does f prime tell you? Well, again, f prime is the rate of change. So it's a slope, right? So it's going to be the ratio of the output, number of deaths, to the ratio of the input, which is days. So this is deaths per day from the coronavirus. So you say like day 10, what is the rate at which the number of deaths is increasing or decreasing? So what is, how many deaths per day on day 10? How many deaths per day on day 11? So that's what f prime represents. So we're taking the area under the curve of f prime here. Okay. So let's just say and again, because of physical context, we want to consider just positive things, right? You can't have negative days. So say that we have a graph of the deaths per day. So let's say it looks something like this. All right. So this is f prime of t, and this is t. So this is in days, and then this is deaths per day. Sorry, it's such a grim topic, but I thought it might be interesting because it relates to what we're talking about. So what the net change theorem is saying is, you know, say this is March, I don't know, 21st. This is April 10th, okay? So these represent so many days from the original day. Let's say like March 1st is day 0, so the day we start counting. So this would in a sense be 21. And then however many more days from here to here, that would be the number for this guy. So I think what, March is 31 days, so 10 plus 10, so 20 days more. So if this is 21, then this would be like 41, or, you know, do you get what I'm saying? So this is kind of like A, and this is like B. All right? So what this is saying is the area under the curve of f prime right here, this is literally just f of b minus f of a. So it's saying is the area is the net number of deaths between March 21st and April 10th. Right? Because capital F of April 10th, that was, remember, F prime was deaths per day, F was deaths. This is deaths up to this day. Okay? And then the same thing, F of March 21st is the number of deaths up to that day. So had 100 people died up to March 1st, and then 1,000 people had died up to April 10th, then you take the 1,000 minus 100, 900. So this is saying that between these 2 days, 900 people have died. So the area under this curve from some point A to B is just the net number of deaths between these 2 days. So that's why it's called the net change theorem. It tells you the net change of the original quantity. So when you take the area under the curve of the derivative, you're getting the net change of the original function. So this is attaching some very meaningful real life example of what's happening right now and how calculus is used in everyday life. And so another good point to bring up here is while we're here, while we're on this train, is why when on the news they were comparing graphs, they were like, we don't want to have this graph right here. If this is the curve that represents deaths per day versus this one, why did they not want to have this super peaky graph? Well, if you calculate the area under this curve is definitely a lot more than the area under this one. So in this scenario, a lot more people are going to die than in this scenario, because the area under the curves are representing the total number of deaths for the course of the epidemic. So if the area under the curve is much smaller, like in this case, this is a much better scenario than this one. So again, this is like, just basic principles of calculus being used in very applicable modern day examples. So that's why, the epidemiologists were like, we don't want this, we want this. This is a lot better. They probably got, very good marks in their calculus courses. I'm glad that they did. Okay, so to move on to like another topic, we can already talked about, how velocity and position play into this as well. So we had the example of a runner. So we had, remember we had a runner, and x of t was the position of the runner. So at time 0, this was 0 meters, because from this origin, this is the origin, 0 seconds into the race, they had not ran any, they were 0 meters away from the origin. But then like later, like so x of 4, so 4 seconds later, maybe this was equal to 16 meters. So they had traveled 16 meters from the origin. Now, this example is good, but it's it doesn't take into account the fact that you can have a negative velocity and what that means. So let's say instead, instead of this runner, you again have an origin, but let's say this is the origin. But you have a particle that kind of goes like all around like this, that's flying around. And you want to measure, how far to the right or to the left of the origin the particle is. So here, if you put like a grid on this, see, in this case, when the particle's traveling this way, it has a positive velocity, because it's positive, it's going in the positive direction, it's going to the right. But then when it ends up turning around and going negative, it has a negative velocity, so it's going like backwards. And also this brings up the difference between displacement versus position, or distance, sorry. Okay, so I can use it myself as an example in this case. So if I am, let's say like, right here, right down here, this is the origin. So if I go one step to the right and then one step back, then how many, steps did I take effectively? That's like distance, is just how far did I travel. So that would be 2 steps. But what was my displacement? How much was I displaced from my original, position is 0. I didn't really move effectively. I went 1 right, 1 left, and I just came back to where I was. So in that case, the sign SIGN is important. So in displacement, I went 1 meter to the right, but then I went 1 meter to the left, or 1 step, sorry. So I effectively have 0 steps. But with the distance, I went 1 meter right, and then I went another, meter to the left, but I still traveled a distance. I still traveled 1 step or 1 meter. So I take its absolute value instead, and I get 2. So with distance, you count both negative and positive positions, being to the right of the origin or going to the left. You count those as positive always, but this one does not. So that's the difference between displacement and distance. So what we can do is, as we discussed last time, this tells us that, you know, if we do have like a particle or something traveling, the net change theorem will tell us this. This is total, absolute value. So that's an and symbol. So see, if we take the absolute value of the velocity, meaning we turn going to the right and to the left positive, which we need to to get displacement, as we talked about, the area under the curve of velocity, which is the derivative of position, this is like x prime. The net change theorem says this should just give us, so if this is x prime, the net change theorem says this should give us x of t2 minus x of t1. So how much I went to the right minus how much I went, you know, these are positions. So you take the net difference of those, okay? But then, you know, if I take the absolute value away, if you take the absolute value away, then this is the total displacement. So big difference. So displacement with, you know, without the absolute value, but if you do have the absolute value, it's distance. So it's kind of important to see the difference, and we can definitely do an example so it's a little less confusing. But given the time constraints, I'll leave that for the next lecture. So definitely maybe think about some of these concepts. You might look up some more stuff about displacement versus distance, but hopefully this gives you a nice feel for it, and we'll do a concrete example next time.